Welcome back to ECE 320A. We're in Unit 12, our two-port parameter unit, and that's coming to us from Chapter 18, and we have homework number 12 and a final exam coming up after we finish this unit. In this particular video, I have a few things that I want to examine, sort of step back. We've already looked at identifying two-port parameters, finding Z parameters for different circuits. We've looked at how you might then analyze a circuit in a terminated two-port scenario. And now what we want to do is try to combine those or illustrate how we might actually be able to utilize these in even more ways. And one of those is to combine two-port networks into one larger, but it still only would then have the 4 parameters associated with it. So our goals first are to essentially convince us that we do have different two-port parameter sets. Where do those come from, and what can we call those, or how can we label those? We'll then illustrate one way of combining two different two ports into one by means of a series combination. And we'll look at how we could also interconnect two ports in both series and parallel forms, and how we can then do that at the input port and the output port, etc. And then we'll finish this video illustrating how we could actually convert from one parameter set to another. And the reason you might want to do that is maybe you are wanting to have everything described in terms of H parameters, and somebody's given you now a set of Z parameters. Well, it might be nice to convert those Z parameters into H parameters. And there's tables that document or give you those formulas. We will go ahead and illustrate how we can convert a set of H parameters into a set of Z parameters in this video. So how many different sets of two-port parameters are there? Here's our definition or diagram illustrating a two-port. We have one port on the left. We might call that the input port, or port 1, and we have a port on the right. And remember, we have these different restrictions. I1 going in on the left has to be I1 coming out at the bottom on the left, coming from right to left on the bottom, and I sub 2 likewise needs to be coming out of the bottom, going from left to right, to satisfy the port current requirement. But we have 4 variables in these two-port parameter setups: I1, V1, I2, and V2. And really it's just a combination situation. How many can we have in terms of different sets if we allow 2 of these 4 variables to be independent at any one time? So really it's a 4 choose 2 if you're into combinations in math, or how many different independent combinations are there, where let's just now say that these on the left will be our independent variables. We could have I1 and I2 as independent. We could have I1 and V1, and we could have I1 and V2. We've run out of sort of ways to combine I1 with I2. I'm sorry, with the other 3. Then we can start combining I2s. I2 with V1, we've already combined I2 and I1. We don't need to worry about that. I2 and V2. And finally, then we have V1 and V2. But once we've shown or identified, and how many did we have? We now have 6. 1, 2, 3, 4, 5, 6 different combinations. The first one with the I's being independent could be labeled as Z parameters. That's essentially Ohm's law. I1 and V1, those in the textbook that we're using are called B parameters. and those you could think of as somewhat like a transmission set. We are worried about I1 and V1, and then we would need to be saying, oh, what's dependent on that? It's I2 and V2. So we're transmitting information from the port 1 to port 2. The third row that we've identified, I1 and V2, this is sort of a mix or a hybrid of port 1 and port 2 variables. We have I1 current and V2 voltage, and that's called the H parameters. Another set of hybrid parameters would then relate I2, the output current, and the input port voltage, V1. Those are a different set of hybrid parameters, and those are labeled as G parameters. We could then talk about A parameters, where now we maybe focus on the output port or port 2 being our independent variables, and those again are like a transmission or an inverse transmission type relationship from port 2 to port 1. And finally, we have the situation where we might consider the voltages, V1 and V2, to be our independent variables. We have the ability to adjust those. So now just think of sources on either side of our 2-port, and inside that 2-port would be our dependent variables, I1 and I2, and those would be related to the V1 and V2 by admittances or Y parameters. Those are the possible sets. We have 6. Now let's look at how we might combine if we had 2 different sets of parameters. Here is one way that we could do it, and this particular way of combining 2 ports, I have a 2-port Z sub A and I have a 2-port Z sub B. Now I have these connected in series. By that I mean that I have at port 1 we have a series connection so that the currents in port 1 and port 2 are the same. This is then labeled as a series connection, and what does that mean if we now tried to aggregate these 2 ports into one 2-port representation? I hope you can see that if we simply enclosed that Z sub A and Z sub B, we would then actually have a larger 2-port, but we would have an I sub 1s. The port current requirement would be true on the left. We would have a V sub 1s being the subscript for series. We have output currents and output voltages on the 2 side or on the right side. And now, is there a way to cleanly describe this highlighted blue 2-port in terms of the starting 2 ports that we began with, Z sub A and Z sub B? Well, what are some relationships? If we look at I sub 1s in this diagram, here's I sub 1s, but that's the same as I sub 1a. But I sub 1a is coming out of 2-port A, but it's also going in as the I1 current in 2-port B, and that's coming out of the bottom, and so that is in fact equal to I sub 1s. So we maintain this port current requirement, and you could do the same logic on the port 2 side of this combination of Z sub A and Z sub B to see that the relationship also holds for I sub 2s. So now we know that those 1s and 2s current-wise are equal. And if we now wanted to know what is V sub 1s, well, V sub 1s, if we simply look at a KVL on the port 1 side, we simply see that V sub 1s is V sub 1a plus V sub 1b. And we can write V sub 1a and V sub 1b in terms of their respective V1 equations in terms of the 1-1s and the 1-2s Z parameters, realizing that I sub 1a, I sub 2a, I sub 1b, and I sub 2b can be interrelated, meaning I sub 1a is equal to I sub 1b, which is equal to I sub 1s. That allows us now to factor out the z11 of a, the z11 of b, and likewise the z12 of a and the z12 of b. That now gives us really a series combination for z11 in the big one, in z11 of s. So this is now, if you wanted to think of it, this is now z11 of s. This is now z12 of s, or the series combination. We could do exactly the same analysis with v sub 2 sub s, and we would find the same relationship. Or we've now collapsed or aggregated two different two-ports in terms of their z parameters into one two-port, where really all we have to do is add the like terms in the two different two-port representations. The 1-1s we add, the 1-2s we add, the 2-1s and the 2-2s we add, and that now allows us, if we have these two-port networks connected in a series connection, meaning port 1 and port 2 are both in series, then their z parameters add. And that's pretty easy analysis to deal with. And it might be that we have the ability to select different parameters or design different pieces of the z sub a and the z sub b separately. We know how they are going to combine in aggregate, and that allows us now to think about the design process from a more top-down perspective. What are some other connections? Well, another connection could be a cascade, where the output port of this two-port, which I've labeled 1, connects to the input ports of port number 2. That could be a transmission type or a cascade type connection strategy. We just illustrated the series, and this favors the z parameters. The z's, combining those were easy. We simply had to add up their respective parameter values. A parallel connection actually favors y parameters. We can simply add the y parameters. If if 2 port 1 and 2 port 2 are both expressed in terms of y parameters, in this particular parallel configuration, we could then just add their admittances in the appropriate y11a with y11b, etc. Here in the parallel, what we're doing is we're actually connecting the top terminals of 2 port 1 with the top terminals of 2 port 2. Likewise, we're connecting the bottom terminals at both the input side and the output side of port 1 with their respective bottom terminals of port 2, input side and output side. We're not connecting inputs and outputs. We're connecting inputs to inputs, outputs to outputs, but we're connecting top to top and bottom to bottom. This is now a parallel. Contrast that with the series, where here we connected bottom to top from 1 to 2. Here in 1 to 2, we connect top to top and bottom to bottom. You can now just imagine the different combinations of connections. We could have a series at port 1 and a parallel combination on the port 2 side. Again, maybe don't get confused. Maybe you could, I'm using the notation in the textbook, I would maybe prefer to call this A and this B. But now if you have 2 port A and 2 port B, on the input side, on the port 1 side, we have a series connection. That's this connection. And on the output side, we have a parallel connection where we're connecting their bottom terminals to each other and their top terminals to each other. Finally, we can talk about a parallel series, where the parallel is port 1 side and the series is the port 2 side, and that's now another way of identifying hybrid parameters. So if you had G parameters, you would, or if you had this interconnection structure, you might want to put these two ports in terms of their G parameters. So if the top two port, let's say A, was expressed as in Z parameters, we might want to convert those to G parameters so that we could then easily combine the top two port with the bottom two port, because if they're both in G parameters, we can simply add their corresponding four elements together. And that's the motivation behind converting between one two-port parameter set and another two-port parameter set. If we were actually combining in series two ports, and maybe the top one was H parameters, we might want to convert those H parameters to Z parameters, and then once we have both two ports in Z parameter form, it's easy to combine those if the interconnection structure is a series interconnection structure. So let's now do that. Let's now examine how we would convert between H parameters and Z parameters. And these conversions are all consolidated or contained in table 18.1. So if we have Z sub A and Z sub B, two different two ports, and we have a series interconnection between Z sub A's two port and Z sub B's two port, it might be more convenient to actually express the bottom two port, which might be now given to us as H parameters, in terms of Z parameters. So let's now convert those H parameters to Z parameters to make the combination, the series interconnection combination of Z sub A and Z sub B cleaner. How could we do that? Here's how we might do it. With H parameters, our independent variables are I1 and V2. And so here are the different four H parameters, H11 through H22. Let's now just move all of those variables to one side of the equal sign, so that now we have H11 I1 plus H12 V2. There's no I2, so we have plus 0 I2 minus V sub 1 equal to 0 from the top equation, correspondingly with the bottom equation. Once we have that, we could actually, now if you love linear algebra, hold on. If you're not too fond of linear algebra, that's okay. We're only dealing with 2x2 matrices, but you can now express those two equations in a slightly different manner by now factoring out the I1 and the I2 on the left and the V1 and the V2 on the right. And we've now identified the appropriate matrix coefficients that need to combine with the I1 and the I2 to produce the appropriately defined V1 and V2 on the right. So equation 1, all we've done is rewritten that as H11I1 equaling V1 minus H12V2. And that's consistent with this top equation. So that is right here, and maybe you need to realize that we are involving both I1 and I2 and V1 and V2 as options. The second equation right here is going to be satisfied by combining these matrix elements with the I1 and I2 and the V1 and the V2. So we have H21I1 minus I2 equaling minus H22V2. No big deal there. We're just rewriting the two equations, the yellow and the blue highlights. But once we have that, now we can solve for V1 and V2 by inverting the matrix that's multiplying V1 and V2 on its left. So if we invert that matrix, and if we assume the existence of that matrix, then we can find the z parameters because now we have V equal to some matrix times I1, I2. And that matrix will be our z parameters. So if this matrix that scales or multiplies the voltages, if it has an inverse, then we can find the z parameters. If that inverse doesn't exist, then we can't find the z parameters for this particular circuit. But assuming that does exist, that matrix does have an inverse, now we simply have to invert that 2 by 2 matrix, which is just 1 over the determinant, and the determinant is not that complicated here. It's 1 times minus H22 minus 0 times minus H12. So we're just left with minus H22 in the bottom. And we interchange the diagonal elements and we change the sign of the off-diagonal elements. We haven't changed this matrix at all. But now in forming that matrix product and leaving the 1 over minus H22 outside so we're not complicating too much, we have this times that to give us this. We also have this times that, second row, second column, to give us this. And we also have the off diagonal. And do I want to go there with this? Maybe I could now say I have row 1 times column 2 would give us this. And likewise, we have row 2 times column 1 giving us this. With those combinations and now pushing this minus sign inside the matrix, we now essentially have our z parameters. Our z parameters, z11 is that numerator over this denominator. And if you look at that numerator, you'll actually see that that's the determinant of the H matrix if we had H11, H12, H21, H22 as a matrix. But here we have Z11, Z12, Z21, and Z22 immediately written in terms of the H parameters. And that's all I'm doing here. I'm saying Z11 is this numerator divided by H22, and that numerator is just the determinant of this H matrix, the H matrix being this matrix of the 4 H parameters divided by H22. Likewise, Z12 is not very involved or complicated. It's simply H12 over H22. Z21 is minus H21 over H22. And Z22 is just the reciprocal of H22. And those are now the Z parameters expressed in terms of the H parameters, which tells us that if somebody was trying to combine two ports in a series interconnected way, and the bottom 2 port was expressed in terms of H parameters, and if that 2 port actually possessed Z parameters, then we could find those Z parameters in terms of these H parameters in this way or from table 18.1. Once we have those, that series connection of two ports written in terms of Z parameters is easy to determine. We simply add up the respective elements in those 2 Z parameter matrices. And that's now the beauty of allowing us to convert between one set of 2 port parameters into another set, and this process can be followed starting with G parameters, with transmission parameters, etc., to determine some set of parameters in terms of another set. And that's how these different conversion tables can be derived. And we have simply shown one way to re-express the z parameters in terms of h parameters in this little video.